Hey everyone, this is Dr. Clyde Letzum again, and today in this video what we're going to do is we're going to look at resistance in circuits and in the body, and this is going to be a three-part series, and this is really a follow-up to the lab on resistance that we have for our physics classes, and it's sort of to help students make a tie-in between what we were doing as it pertains to resistance in circuits and how that information can be carried on over to the body, and we can talk about resistance within the body as it relates to the cardiovascular system. Alright, so what we're going to do is first we're going to look at this circuit here. And this looks very similar to the circuit that we kind of set up in class. The only difference is over on the very far right side, I put this cloud in here. What this cloud simply means is this. It's the rest of the circuit that we really don't care about, okay? What we really care about here is we want to figure out what the resistance through this component is. Now, in order to figure out what the resistance to this component is we can actually check the voltage that's seen across that component and check the current that's actually going through that component, the current that's actually being generated from this voltage supply here. Okay, so if you recall from the lab, if you don't, if you're not in my lab, you may know Ohm's law, and it says that the voltage is equal to the current, which is indicated by the letter I, times the resistance. Okay, voltage is equal to current times the resistance. Now, what I didn't mention during our lab is that really the full equation here really says that the change in voltage, okay, across some given component is equal to the current that passes through that component times the resistance of that component. So what exactly do we mean here by that change in the voltage? So what it means by change in the voltage is that the voltage as seen across, again, that component, in this case here, the voltage at the beginning of the component minus the voltage at the end. So it's the difference between the voltage as seen at this point versus the voltage as seen at that point. So in other words, which is equal to the voltage that's being dropped from here to here. The voltage being dropped within the actual component itself. So that VA minus the VB is equal to, again, I times R. All right. And so what this means then, if I want to find the resistance that's in this component, if I know what the voltage is at the beginning here, and the voltage is at the end here, or in other words, the difference between the voltages, which is what I will find with a voltmeter if I connect it across that component here in this fashion, and I know what the current going through that component is, and I can find it by connecting the ammeter in series with that component, because the current, remember, in series is going to be the same, then I can take that voltage drop across those two, and this should be a lowercase b. I can take that voltage drop across those two divided by the current passing through that component, and I will be able to find the resistance. Okay, so that was an example of just the circuit that we set up in class. So now let's take a look now at how we can actually take that information and sort of relate it to what's going on in the body and the cardiovascular system. All right, so in this case, what we're looking at here is we have a blood vessel, or part of a blood vessel. And inside this blood vessel, we have a buildup of calcium that's in here. Okay, the calcium is represented by this yellow area that's here. So if we have a buildup of calcium in that area, and over here I should mention also we have some force. In this case, it's a force being generated by the heart pushing the blood through this blood vessel, and this blood vessel, by the way, has a cross-sectional area represented here by the red here and the red over here. Okay, what is going to happen then if I have, remember from our equation in one of our previous labs, if you want to figure out what the pressure is, okay, you can take the force divided by the cross-sectional area, and that'll tell you what the pressure is. So if you think about this portion of the the blood vessel over here, what happens is if I know what the force is and I know what the cross-sectional area is, then I can figure out what this pressure is right here. Now, what you'll notice, though, is that that cross-sectional area, if this has calcium in it, is actually going to get smaller and smaller as you end up going towards from left to right in the blood vessel that's here. If that's the case, then what happens as you're moving from left to right in this area, that cross-sectional area is getting smaller. Now remember, because the cross-sectional area is in a denominator, what this means is that you have an inverse relationship between these two. And so as the cross-sectional area decreases, what this means then is that the pressure over here increases. And then if we go over on this side, you'll notice that the cross-sectional area starts to become big again as there's less calcification or less calcium over here in this part of the blood vessel. So as the A increases, what happens over here is the blood pressure, or the pressure over on this side, decreases. So when that happens, then what we're saying then is that the pressure over on this side, PA, is larger than the pressure over on this side, which is PB. And so we can figure out what the pressure is, the pressure differential between what's going on this side versus what's going on this side, PA versus PB, or side A versus side B, by using the delta P, meaning we're going to take the difference between the pressure on the left side here, PA, and the pressure versus the pressure on the right side here, PB. Now, if we take that information, okay, and I guess part of my equation is cut off here, but I'll go ahead and tell you what it is. If we take that equation, if we know what the flow rate is, the amount of blood that's actually flowing past this calcification here, and we're going to use the letter Q to represent the flow of blood, okay, what that says then is that if we know that flow rate that passes through there, the calcification area, then we can approximate what the resistance of the blood is within that area. And the resistance of that blood then is going to be equal to that pressure differential, okay, divided by that flow rate, which is Q, and that's going to be equal to our resistance. So it's very similar to the equation that we had before in the previous slide, where you had the difference in the voltages divided by the current, which was I, and that gave us a resistance. In this case, the difference in the pressure, okay, PA minus PB, divided by the Q, okay, Q, which is the flow of the blood, or flow rate of the blood, is equal to R, okay, which is our resistance. So again, that is a explanation as to how we can relate resistance in terms of what we've been working with circuits in resistance as it pertains to the body. So again, this was a demonstration or a presentation on resistance in circuits and in the body, and this is part 1 of the series. And again, my name is Dr. Clyde. Please do check out part 2 and part 3. They should be very useful when it comes to your lab related information.